From the air, this looks like somebody flooded a desert. White dunes run to the horizon. Between them, blue lakes appear by the thousands. They have no rivers flowing in, they have no rivers flowing out. Months later, many of them are gone, and the dunes around them have moved. This is not a computer render. It is a national park on Brazil's Atlantic coast. Its name is Lençóis Maranhenses. Lençóis means sheets for the pale folds of sand, but the name does not explain the water. In a wet year, official park material says more than 36,000 lagoons can form. That is an estimate, not a permanent lake census. The number changes as the landscape changes. To understand it, start with the first wrong assumption. This is not a normal desert. A true desert is defined mainly by a severe shortage of precipitation. Lençóis merely wears the costume, bare sand, sharp ridges, and almost no shade. Its climate is tropical and semi-humid. The UNESCO evaluation reports annual rainfall that can reach roughly 2 meters, concentrated mainly in the first half of the year. That is enough water to make the word desert misleading. During the rainy months, storm after storm falls on a dune field beside the Atlantic. The protected property covers about 156,000 hectares. Roughly 90,000 hectares are dunes, an enormous reservoir of sand with thousands of low spaces between ridges. So rain itself is not the mystery. The mystery is why loose sand material famous for draining quickly can hold visible water for months. The answer sits below the surface. But before going underground, we need to explain why this much sand is sitting beside a rainy tropical coast. Because these dunes are not the remains of some ancient inland Sahara. They belong to a living coastal conveyor belt. Rivers carry weathered sediment toward the Brazilian coast. Near the ocean, waves and coastal currents sort and redistribute that material along the shoreline. When exposed sand dries, persistent trade winds can lift the finer grains and drive them inland. Grain by grain, the coast feeds the dune field. A dune grows where moving sand loses speed and falls. As wind pushes grains up the gentle side, they tumble down the steeper lee face. That simple cycle translates the entire ridge. More sand arrives from behind, while the front advances over whatever lies in its path. The exact contribution of individual rivers is complicated, so the defensible story is a system: river sediment, marine reworking, shoreline supply, then wind. Seen from above, the result resembles frozen waves. It is the opposite. Every ridge records motion, and the water must fit inside a surface that refuses to stay still. Now return to the rain. If the upper dunes are permeable, why does the water not simply disappear downward? Picture a slice through the landscape. Rain lands on the dune and infiltrates the sand. Underneath is groundwater whose height rises and falls with the season. During the wet months, recharge arrives faster than the system can lose water. The water table climbs toward the floors of the interdune depressions. When that saturated zone reaches a depression, groundwater and surface water meet. The low basin fills even though the sand above it remains permeable. This is more useful than imagining thousands of perfectly sealed clay bowls. Deeper bedrock and less permeable material can slow drainage, but the moving water table is central. Each lagoon is therefore a visible window into groundwater. Its shoreline marks the intersection between a curved sand surface and a temporary underground level. Small differences in dune height create different basin shapes. One fills as a narrow ribbon, another becomes a broad turquoise pool. Nearby high ground stays dry. The lagoons are described as rain-fed, without permanent inlets or outlets. Yet their shapes echo a hidden connected system beneath and between the dunes. And because both sides of that intersection can move, the water vertically and the sand horizontally, no lagoon has a guaranteed permanent outline. Lakes are not sitting inside a fixed landscape. Wind drives grains up one face and drops them down the other, slowly shifting the ridge. Authoritative summaries report migration of roughly 4 to 25 meters per year depending on the dune, its position, sand supply, vegetation, and wind conditions. 25 meters is not the speed of every dune, but at the upper end, a ridge can advance about the length of a swimming pool in 1 year. That movement changes the depth and orientation of interdune basins. A low place can narrow, open, split, or be replaced as neighboring ridges migrate. Vegetation marks part of the contest. Roots can stabilize sand near margins and islands, while exposed central dunes remain more mobile under strong seasonal winds. The dry season makes that motion easier to see. Fine grains stream from crests like smoke, revealing that a dune is a flow, not an object. So, when the next rainy season arrives, water may return to a geometry that did not exist in quite the same form the year before. As the rainy period ends, the balance reverses. Rainfall drops, sunlight and wind continue removing water, and the regional water table begins to fall. The lagoon surface sinks with it. Broad pools retreat from their margins, narrow connections break, and exposed wet sand expands around the remaining water. Eventually, many basins become dry enough to look like ordinary gaps between dunes. Their water has evaporated or returned below the visible surface. Not every lagoon follows the same schedule. UNESCO material distinguishes temporary and more persistent lagoons, so saying every lake disappears would be wrong. Depth, basin shape, recent rainfall, groundwater position, wind, and evaporation all matter. Two neighboring lagoons can reach the dry season with different amounts of water. This is why a single aerial photograph can mislead. It freezes one moment in a system whose most important variable is time. But when the water contracts, it creates a biological problem that sand and hydrology alone cannot answer. Some of these lagoons contain fish. A scientific inventory recorded 49 fish species in the park and adjacent waters. That does not mean 49 species occupy every temporary lagoon. It does mean this dune field is not an isolated collection of sterile swimming pools. It sits inside a broader network of rivers, streams, wetlands, and longer-lived water. During high water, temporary connections and flooded low ground could open routes that disappear later. Fish can recolonize some lagoons when those routes return. Other animals may persist in deeper or more permanent refuges. Different species and different basins need not use the same solution. A popular explanation says fish simply bury themselves under every dry lagoon, or that dormant eggs wait everywhere beneath the sand. The evidence does not support that universal story. Authoritative popular material describes Trachera surviving in damp substrate, but that narrow claim cannot explain an entire regional fish community by itself. The honest answer is more interesting. Persistence, reconnection, and recolonization operate together, while species-specific survival remains an active ecological question. A disappearing lagoon is therefore not necessarily a biological dead end. It is one temporary room in a landscape that periodically reconnects. Now, the impossible image has a mechanism. Rivers in the Atlantic help supply and sort sediment. Wind builds that sand into migrating dunes. Seasonal rain infiltrates the field and raises groundwater. The water table reaches low interdune floors, turning them into thousands of freshwater lagoons. Then rainfall eases. Evaporation continues, groundwater falls, and many lagoons contract or disappear while the exposed dunes keep moving. Organisms persist in the more complicated network around those temporary waters, ready to expand again when seasonal connections return. Lençóis Maranhenses is not extraordinary because a desert somehow breaks the rules. It is extraordinary because it was never the static desert the image suggests. It is coast, aquifer, dune field, wetland, and wind machine occupying the same place, each process changing the stage for the next. What makes these thousands of lakes feel impossible is also what makes them temporary. Almost nothing here stays where it was.